Hey everyone, and welcome to The Explainer. Let's jump right in. Today, we're tackling Section 9.4, Representing Simple Functions, and we're going to completely reframe how you look at abstract algebra by turning it into something you can literally picture in your head, like a predictable, logical assembly line. We're talking inputs, outputs, the whole shebang. So let's get into how mapping all this out really opens up a window into the core logic of math.
Since math builds on itself, here's our roadmap for today. We'll meet the function machine, visualize the data, translate things into algebra, scale up to two-step machines, and finally, master inverse functions.
All right, Section 1, meet the function machine, building the foundation.
To really wrap your head around functions, I want you to imagine a literal conveyor belt. A number drops in on one side, we call that the input, right? Then a specific mechanical process happens inside this box, and boom, a completely new number pops out the other side as the output. So what exactly is going on inside that black box to make the number change?
Well, let's look at a super basic function machine. The input, which we usually call x, goes into a machine that has one clear rule: multiply by 3. Then, it spits out the output, our y. So, if you were to toss a 4 into this machine, it obediently multiplies it by 3 and out pops a 12.
Now, here's the absolutely crucial takeaway. A function is never just random. By definition, it's a strict mathematical rule. It guarantees a specific, highly predictable output every single time you feed it an input. Honestly, it's this exact consistency that makes modeling real-world processes actually work.
Moving on to Section 2, Visualizing Data, Drawing Mapping Diagrams.
Take a look at how our function machine seamlessly turns into a mapping diagram. The machine tells us the rule is to divide by 4, right? While the mapping diagram physically draws a line from the top row of inputs straight down to the bottom row of outputs. It's just a fantastic visual way to prove that this relationship holds true across a whole sequence of numbers. But, let's say you've got a ton of data. To keep things clean without completely overwhelming our workspace with a crazy web of lines and arrows, we can organize multiple data points using an input and output table. By lining up our inputs, the rule, and our outputs, the table instantly reveals that underlying pattern. And having multiple pairs of values ensures the function we're looking at isn't just a coincidence, but genuinely represents the math.
Let's head into Section 3, Translating to Algebra, the universal language of math. Okay, pictures and tables are great for sure, but mathematicians, they love efficiency. By translating our factory machine into an algebraic equation, we just use the letter x for inputs and y for outputs. So an add 5 machine perfectly translates to the equation y equals x plus 5. Usually we write these starting with y equals, just to clearly define what the final product of our factory actually is.
And let's quickly clarify what an equation is, because it's a real game changer. Unlike a basic expression, which is really just a statement like x plus 5, an equation is powerful because it literally contains an equal sign. That one little symbol is the magic key that lets us actually solve for our unknown output values perfectly every single time.
All right, Section 4, Two-Step Function Machines, Scaling Up the Complexity. So now, instead of just one operation, we're looking at an advanced machine that requires our input to pass through 2 distinct phases before it becomes an output. First, the input enters a chamber where it gets multiplied by 2. Then that brand new number immediately moves into a second chamber where 1 is subtracted from it.
Narrating exactly how this works sequentially really helps us process the cognitive load. By writing it out clearly, Step 1, multiply by 2. Step 2, subtract 1. We make sure we don't trip up on the order of operations when things start getting a bit complicated.
So let's actually test it. By carefully walking through the formula step by step, we see that an input of 2 perfectly yields an output of 3. 2 times 2 is 4, minus 1 is 3. This proves our complex machine is functioning exactly as it was designed to. The algebra just beautifully mirrors the mechanical steps of our factory.
Finally, Section 5. Mastering inverse functions, hacking the machine.
So what is an inverse function? Well, it's basically a reverse equation used to work backwards from an output to find your original input value, and it is incredibly useful. Just imagine you only have the final product, the output y, but you really need to know where it started. An inverse function lets you run the whole assembly line in reverse to discover that original input.
But pulling this off requires some discipline. Following specific rules of reversal ensures we accurately untangle the math. We literally have to read the machine backwards, from right to left. And crucially, we have to do the exact opposite of the original instructions, changing plus signs to minus signs, minus to plus, multiplication to division, and division back to multiplication.
You can easily see this reversal in action right here. If we have a standard equation like y equals 6x, well, our machine originally multiplies the input by 6. To find the inverse equation, we hack it by doing the total opposite. We take our output y and we divide it by 6, which gets us right back to our original x.
Now you might be wondering, why does any of this matter outside of a math classroom? Well, it's because these highly predictable input and output functions are literally the foundation of the complex algorithms that govern our digital lives. They predict our behavior online by tracking metrics like share, subscriptions to determine exactly what content we are fed next. Every single time you click, you are an input dropping into a massive function machine.
So I'll leave you with this final thought. Knowing what you now know about mapping diagrams, two-step machines, and inverse equations, how might you apply this to the world around you? Can you work backwards from the outputs you see every single day to discover the hidden inputs controlling them? Thanks so much for joining me for this explainer. Keep asking questions, and I'll catch you next time.